In this video, I will be talking about anti-aliasing CNNs, aka blur pool. This paper is a simple trick that can be used to make CNNs more robust to translational changes. And this is a very simple idea that I'm surprised it took us till 2019 to come up with it. What is the problem with current CNNs? The problem is that small translational changes in the input image or input features lead to significant changes in the output of the pooling layers. This is demonstrated in a simple 1D example in the image below. The gray line that you see, let's consider that to be the input. Based on which two samples of this input we consider for max pooling, the output drastically changes. If we take one combination, the output is going to be like what you see in blue squares. But if we pick those two samples starting at a different point, what we see for the max pool output is going to be more like the red squares. This is not a good property for a network to have. Small changes in input causing notable changes in activations. This paper proposes a layer to solve this issue. Yes, we see the problem with CNN in a toy example, but does this happen in an actual CNN that is trained on ImageNet? The authors showed that this actually happens. What you see here on the x-axis is the number of pixels by which the image is shifted in the diagonal direction. And what you see in the y direction is the probability of the correct class that is predicted. As you can see in the black line, what happens as we are moving the input image is we see this periodic behavior where you have correct predictions and wrong predictions based on how the image has been translated. This is not a good property to have. The blue line here is what you get when you use the CNN layer that is proposed in this paper. Are we sure that max pooling is responsible for this problem? The authors visualize the features of the CNN to confirm this. They feed the CNN both of these images with translational shifts and see at which layers is their highest difference in activations. And what they see is that the activation gets maximized at the pooling layers. The authors propose that this problem can be solved by doing a max blur pool instead. So the idea is we still do the max operation, and every time before pooling we do a blur operation. And as you can see on the right here, this leads to a much more stable output even with slight translational changes in the input. This slide shows what we are doing in more detail. We are using an anti-aliasing filter or a blur kernel right before subsampling. The authors showed that this kind of blur pooling can also be applied to other layers other than max pooling. Any layer that does downsampling, for example, an average pool or a convolution with stride 2 can be benefited by including blur pool in the following way. The results of using blur pool is shown in these plots. We see the results of using the blur pool layer in blue, and we see the results of not using it in black. As we can see, the accuracy for black goes up and down as we are translating the image, whereas it remains quite stable for the blur pool layer. And this is true across networks and across datasets. The authors run additional sanity checks just like before and confirm that the issues that were existing with the traditional CNN do not exist anymore when we use the blur pool trick. The authors define a metric of consistency and show that the consistency increases for a wide range of blur pool kernels. Does blur pool also work for non-classification tasks? The authors explore this by generating images using the pix-to-pix network. The pix-to-pix network remains the same in both the baseline and the author's architecture, except that all the downsampling layers are replaced by the blur pool layer. And as you can see here, as we're changing the input, the output generated is much more consistent when we use the blur pool layer. That's the end of this video. Thank you.